Welcome to Testing, a brand new podcast that examines important changes in the field of education with help from leading researchers, practitioners, and government officials. Our show looks at data on the margins to understand how learning happens and how individuals and institutions can support more of it. Sometimes we review projects, and other times we review policies. But whenever you tune into Testing, we always hope to provide you with some new perspective, whether on the impact of artificial intelligence or a bipartisan bill in the Senate. My name is Michael McKay, and I will be your host. I'm Master of Education, at least on paper. In practice, I still have a few issues from teaching ancient Greek and Latin. This fall, I hope you will join me in heading back to school.
America's future depends on its teachers.
We've always had a love affair with learning in this country.
The educated citizen has a special obligation to encourage the pursuit of learning, to promote
Testing is supported by Epigrammer, an AI-powered teaching tool that helps instructors make and grade assessments by comparing students' notes and instructors' feedback on graded assignments. When I taught classics, I struggled to provide effective feedback at scale, so I co-founded Epigrammer. With this podcast, I hope you'll test some of your assumptions about what it means to get an education. How do you know what you know? In Hamlet, a guard confronts an apparition before the palace. He asks, "Who's there?" Another guard responds, "Stand and unfold yourself." The tragedy begins with this question, and the subsequent command provides a method for answering it. The audience will know who's there based on what can be seen on stage. Later in the scene, Horatio will appear on stage and ask the ghost to identify himself, but the phantom will only exit silently after hearing "stay, speak, speak." When we consider how we know what we know, we are often left with images. The first guard sees what looks like the deceased king of Denmark and tells Horatio to mark it. Horatio then refers to the ghost as if it were Hamlet's father. But what happens when the ghost is not on stage but inside one of the players? Enter Quinn Squires, co-host and producer of Testing.
This week, we met with Dr. Lauren Emberson, a neuroscientist at Princeton University, to tackle the question of how we know what we know.
As a graduate student, I encountered Dr. Emberson's 2015 paper that broke new ground on how the human brain learns. Importantly, her 2015 study was the first to link infants' neural strategies with those of adults by using a technique called FNIRS. But first, a brief lesson on statistical learning. So, Quinn, I need you to listen to the following audio from a classic word segmentation experiment at the University of Wisconsin-Madison, and then answer a few questions. For the record, all of those listening at home can join in too.
Bi go ku bu la do ta du ba da ti ba bu la do ta du ba bi go ku da ti ba bi go ku ta du ba da ti ba bu la do bi go ku ta du. Which of the following sequences of syllables is a word and which are non-words? Bu la do bi ti ba ta do bi go ku.
Now, let me grade your work, and just as I suspected, you're about as clever as a baby.
Hey!
That's actually a good thing, because babies are quite good at statistical learning.
Which is...
I'll let Dr. Emberson explain.
Statistical learning is a phenomenon where, starting from very early in your life all the way until quite late in your life, we're able to take patterns in the environment that show up as parts of statistics in our sensory input, like what you see, what you hear, what you touch, and we're able to learn from them.
I'm still not sure I get it.
So I'll give you a specific example that really launched the study of this phenomenon. When you're a baby and you're learning language, you hear just the stream of sound. You don't know any words. You don't know any kind of structure to what you're hearing. But the syllables start to co-occur. So if you take the phrase happy baby, ha and p occur together quite a bit. Be and b occur together quite a bit. But the syllables that span the words do not, because you can have many happy things: happy dog, happy person, happy researcher. You can have many babies, right? Pretty baby, handsome baby, smart baby, etc. And it's that combination of those very highly predictable and not very predictable types of information that infants and adults can learn from.
Can you tell us more about research projects going on here at the Princeton Baby Lab?
This is a lab that's co-directed with Dr. Casey Lou Williams. Both Dr. Lou Williams and I are specialists in the area of statistical learning from different perspectives. And so because of that, we have a broad range of studies that are happening here, all the way from studies looking at, and would be my specialty, the neural bases of how learning unfolds, what the consequences of this learning is, starting extremely early in life, specifically the first couple days of life outside of the womb. And we have a lot of other studies looking at what the perceptual consequences of this are, what the consequences of this types of learning are for language, for example, the words that you know, the grammar that you understand, as well as, and this is spanning into Dr. Lou Williams' work, the social scaffolding that babies use to try to do this type of learning as well. Do they do statistical learning better if it's being conveyed to them by a speaker that they know, a language they understand, or is it something different?
And something different was what Dr. Emberson and her colleagues found in 2015. Published in the Proceedings of the National Academy of Sciences, their paper, Top-Down Modulation in the Infant Brain, Learning-Induced Expectations Rapidly Affect the Sensory Cortex at 6 months, was significant because it was the first to identify how even early-stage learners can leverage sophisticated top-down feedback neural strategies. Now, what are sophisticated top-down feedback neural strategies? Broadly speaking, top-down or deductive reasoning uses background knowledge to influence our perception. So an example of this that you've probably come across is word jumbles. You can still read a sentence where every word's letters seem jumbled because you're such an expert at reading English. So your prior knowledge shapes your perception or cognitive understanding of what you're reading, even if there are missing words or typos. Sophisticated top-down feedback neural strategies are what we take for granted as adults. When we see the ghost of Hamlet's father appear on stage, our brain's occipital cortex lights up with activity, and we continue to track that sudden surprise until the ghost disappears. But how do we know what is surprising to a baby? Let's play one more game, loosely based on Dr. Emberson's 2015 experiment. Now, I'm going to play two sounds, so if you are listening to this podcast on your phone, I will need you to look at your phone and start shaking it. Now, you probably weren't expecting that second sound because I primed you for rattling. In other words, the horns didn't align with the image in your head associated with shaking. Similarly, Dr. Emberson's team used both of these sounds to probe how babies learn. In terms of research techniques, can you tell us more about why you used functional near-infrared spectroscopy, or FNIRS?
Absolutely. So functional near-infrared spectroscopy, or FNIRS, the much easier way to say it, FNIRS, it's a technique of essentially doing fMRI with babies. Let me start by motivating why fMRI doesn't work with babies. So for all of your listeners who's ever been in an MR scanner for whatever type of scan, you know that it's a confined space, it's an extremely noisy space, and something where you cannot move at all. And so if any of your listeners have spent any time with babies or children, they see why this is very challenging. And yet, we want to understand the function of the infant brain, and fMRI is the tool right now to understand function, and specifically what parts of the brain are doing what. So given that we want to understand what the function of babies' brains are, and that we can't do fMRI, this new technique has really emerged, FNIRS. It records the same physiological signals that fMRI records, and that's specifically changes of oxygenation in the brain. You don't often hear this when you talk about NIRS studies, but that's all it's recording. It's not recording anything to do with neural activity, but the sophisticated interrelationship between how your brain uses oxygen when it works hard. The analogy you can make is it's very much like a muscle. If you flex a muscle quite a bit, your circulatory system is going to compensate and flood that area with new oxygenated blood to support the movement of that muscle. And your brain, it turns out, is no different. And so what fMRI records is how your circulatory system is changing in response to neural activity. And then we can say, aha, that part of your brain is working very hard. NIRS does the same thing. It records that signal. It does it using light instead of magnetic fields. That light is able to actually penetrate through your skull in a way that doesn't harm anyone. It's entirely biologically inert. And it actually touches the surface of the brain to record changes of oxygenation in the surface of the cortex. So that's how we're able to record the same physiological basis of fMRI, but now with babies, we put these little caps containing lights and record these changes of oxygenation. What this allows us to do, because now we're outside of the scanner environment, is to put these caps on babies and say, here, baby, here's something new to learn. I want to understand how your brain is doing it. Okay, baby, why don't you interact with your caregiver? Why don't you look at this picture and we can understand the function of infants' brains as they're actually using them?
What have been some of your more recent surprises in investigating this topic at Princeton?
So I'm going to be a little self-serving and say it's partly related to this 2015 paper that you guys are really building on.
Sure.
And I'll connect it to something else in a moment. But with that paper, the one thing we really understood about babies' brains at that point was that they're really poorly connected. All of that work is from fMRI while babies are in the scanner while they're asleep. And so we know mostly about the structure of babies' brains. We know that they're very poorly connected. They don't share information between areas all that well. And so you'd think, well, how would you ever learn in that case? Learning must look very different, and specifically different than how adults do it, which is all about sharing information around the brain. And so what we found using NIRS is to see over and over again babies surprise you and how much information they can share around their brains and how much of their brains they're using. Their frontal lobes are not silent at all. And again, this is the region that you think of as being the slowest to develop, the most sort of mature, high-level region that we have in our brains. A lot of researchers point to this region as being why humans are different in our cognitive abilities compared to chimps, for example. And yet, very young babies, there's been research both from myself, but many other labs as well, showing 3-month-olds are using their frontal lobe to do all sorts of sophisticated things. Now, not to say that babies' cognition is hugely sophisticated, but they're using these sophisticated regions to learn and to change how they process stimuli different, how they respond to stimuli differently. And so that's also been surprising, that babies' brains are just incredibly active, incredibly engaged from the get-go.
Sequin, when I said that it was a good thing you were as clever as a baby, what I meant was that you demonstrated a surprising amount of activity in your frontal lobe.
You know, I could probably demonstrate even more activity with a good night's sleep.
But then what will we do with all these babies?
For the record, there are no babies in this studio.
For the record, there is no studio.
Okay, let's just go back to Princeton.
What initially drew you to this field of research, or what are your strongest motivations in digging more deeply into the problems that this research poses?
Yeah. So at the end of the day, I want to understand how we see the world. I see perception as an incredible ability that's really undervalued. And I actually think education is a perfect place where I think it's undervalued, right? We think a lot about cognition. We think about learning and memory. We think about your frontal lobes, what they're doing. They're inhibiting this response. They're tracking this pattern. But your perceptual systems are exquisitely tuned, not just to the environment that you were raised in, but the specific demands the environment has placed on you. I'm going to give an example that I think is intuitive to a lot of adults. If you're like me and you know a little bit about wine, but not very much, and you're around someone who knows a huge amount about wine, they're tasting things of that wine, or they say so anyway, that is nothing like what you can experience. That's a type of perceptual expertise which parallels all the expertise that we have for seeing faces, understanding language, just seeing the world around you. Now think if that was gone, right? The rest of your cognitive abilities are going to be hamstrung by that. Your perceptual systems are exquisitely tuned, and that's part of why our cognition and our learning is so incredible. And so I want to understand this in developmental context, why this happens, how this happens, and what this gives babies, and why that's so important to all the rest of the cognitive abilities that we have. Everything they learn, language, everything else. Perception is the building block that it's founded on, and it's also exquisitely sophisticated on its own. So that's really how I ended up here. And I have to say, originally I was not a developmentalist. I didn't study learning at all. And the more I started opening that box of trying to understand it, I feel like it's one of the greatest mysteries and the most important thing to understand in the world. And so that's why I'm still here many, many years later.
That's great. As we put a footnote on a paper which we've been focusing this podcast on and digging into the science for that, is there anything in that study that you would want to continue building on?
I would say one of the most important next steps that we have is to take these findings that are very much in the lab and understand what it's giving babies, right? So getting there is, saying, understanding what's happening next increases their perception by 15%, which is much larger than we anticipated. That's nice. But we're in the lab, right? And babies are sophisticated operators, both in the lab and out. Is this something that they're actually using to help them? And to understand, not only does it help a typically developing baby, but how these sorts of phenomena and how these sorts of underlying mechanisms of development are changing for babies who are going to struggle or who are at risk. So some of our work is looking at babies who are born very and extremely prematurely. We know that babies in that group go on to have language deficits and lots of problems in school. Not all by any means, but they're certainly at risk for it. You also tend to see that how their brains process language, for example, is quite different. Are these some of the bases for why that happens? As well as, for example, infants that are being raised in impoverished environments, you similarly see some of these types of learning abilities, prediction abilities are impaired. I would love to be able to track and interrelate what we're doing in the lab with those populations, as well as with just babies at large, to say, if we can uncover the cognitive bases of some of these difficulties that they have many, many, many years later, and we can see them in neonates, 6-month-olds. Maybe this is something where they never have to struggle at all. Maybe we can help to train these babies when they're 6 months old, 1 year old, and they'll never miss a developmental milestone. That would be the hope, and that would both, of course, better the world hugely and also show us that we understand what's going on. That's a pie in the sky goal, but that's where we want to go.
So, Mike.
Quinn.
Obviously, babies are not good for the world.
And all the world's a stage.
But what if those babies were cybernetically augmented with neural nets and staged a coup?
That's a really specific question, Quinn. But I did ask Dr. Emberson something similar. One last question, Dr. Emberson. Can you speak more about the impact that this research may have on the field of machine learning?
Absolutely. So a colleague of mine that I talk to fairly frequently is very interested in specifically deep neural nets, and how the development of deep neural nets that recognize objects and pictures. So, for example, I can show you a picture of a bunny on a field with some trees and everything else, and this particular neural network is able to recognize that bunny is there. Now, that's a high-level visual phenomenon. And when you train a network to do that, it looks a lot like the human visual system, and it seems like in some ways it develops similar to the visual system. And the question is, what signals is that network using, and is it similar to the signals that we've been uncovering in babies and how they're using? I certainly think that there can be a huge amount of intersection between the two. At this point, I would say in my experience, it's mostly in terms of this crosstalk of, isn't it interesting to find these parallels, and how neat would it be to integrate it? By and large, I think, and again, this is related to my work, but I would love to see what we found in infants be employed, and to see whether in the context of these neural networks, for example, or machine learning algorithms, to say, does that change or constrain how learning operates? That brings that learning to be closer and closer to being biological, to being human. It might reduce the power of that learning, for example, but it'll help us quite a bit to understand how human learning operates, for example. Could also potentially make that learning hugely more powerful. We know humans are incredible learners, right? That's what my work and many other people's work is showing.
Well, that's appropriate then that it's at its infancy, given that that's the topic for the show. Yeah. Well, we'll keep an eye out for that research and come back here at that point in time to do another podcast on that specific study.
Great. I look forward to it.
Thank you so much for being here with us today, Dr. Emberson. We really appreciate your time.
My pleasure.
You know, I think we should do our next episode on puppies.
Well, Quinn, you're a sick puppy, and we're doing it on machines. To learn more about guests on Testing, visit us at testingtesting.fm. There, you will find helpful links to episodes released each week on Apple Podcasts. Or, to learn more about your hosts, take our personality quiz. If you would like to comment on an episode or correct a record in some way as well, write our team at writing@testingtesting.fm. That first writing starts with an R. But for now, pencils down. I'll see you next week